Hello, let's solve this question. Given two particles of masses m1 and m2 are at d distance apart, due to gravitational attraction, they move towards each other. What is the speed of m1 when their separation reduces to d by 2? So here it's a two-body problem. We can reduce this to one-body problem using the concept of reduced mass, right? So let's consider, because it's given to find the velocity of mass, a body of mass m1. Let's consider m2 is at rest. Then relative acceleration is force by reduced mass, which is m1 m2 by m1 plus m2, and the gravitational attraction between these two bodies is g m1 plus m2 by x square, right? I mean, the two bodies of masses m1 m2 are at a distance of d apart at the beginning. After a certain time, that is certain arbitrary time, these masses m1 and m2 will be at a distance of x, right? We need to find when the separation is d by 2, what is the velocity of mass m1. So this is m1 m2, right? This is m1 m2 will get cancelled. Then this will be g into m1 plus m2 by x square. Fine. As we know that acceleration is dv by dt, which can be written as dv by dx into dx by dt. This dx by dt is v, this is dv by dx. So then a12 becomes v12 into dv12 by dx, which is equal to g into m1 plus m2 by x square. As you can see, this dv12 by dx, right? As you can see at the beginning, the distance between these two bodies is d. As the time passes, because of the gravitational attraction between these two bodies, potential energy decreases, kinetic energy increases, which is v square increases, right? Then velocity increases, but the separation between these two bodies is getting decreased. So dv12 is positive, but dx is negative. And the change in velocity is positive, but the change in positions are, the distance getting reduced, right? So this v12 dv12 by dx, there will be a minus sign, right? Equal to g into m1 plus m2 by x square. So this is minus v12 dv12 equal to g into m1 plus m2 into 1 by x square dx. Let's apply the integrations here. At the beginning, it has d distance apart. We need to figure out at d by 2. So at the beginning, they have a kinetic energy of 0, and at the distance of d by 2, it's v12. Then this is minus v12 square by 2 equal to g into m1 plus m2 into integration of 1 by x square is, it's x power minus 2 plus 1 by minus 2 plus 1, which is minus 1 by x into integration limits are d to d by 2. This minus will get cancelled. Then this is v12 square by 2 equal to g into m1 plus m2 into, this is x is 1 by x, right? 1 by d by 2, which is 2 by d minus 1 by d, which is then v12 square equal to 2 into g m1 plus m2 into 2 by d minus 1 by d is d. So this will be v12 equal to root of 2g m1 plus m2 by d. Here v2 is relative velocity between these two bodies, right? We can use, as here it's net external force is equal to Newton's second law dp by dt. As there is no net external force acting on the body, this is 0. If dp by dt is 0, then p is conserved, right? P is conserved, right? Then momentum at the final and the, I mean, momentum is conserved. The final beginning momentum will be the same. Then m1 un plus m2 u2 equal to m1 v1 plus m2 v2, right? This is m1 u1 bar plus m2 u2 bar is m1 v1 bar plus m2 v2 bar. As this at the beginning these two are at rest, this will be 0. As v2 bar and v1 bar are in the opposite direction, so I mean, they are in the same line, so we can take it as m1 v1 minus m2 v2 equal to 0. Then we need to figure the velocity of v1, right? So that implies v2 equal to m1 v1 by m2. Right? Here, as you can see here, it's v12 is, which is v12 is v1 minus of minus v2, right? Which is, I mean, they are moving in the opposite direction, relative velocity, which is v1 plus v2 is root of 2g into m1 plus m2 by d. Here v2 is m1 by m2, right? And we have taken the common of v1 is equal to root of 2g m1 plus m2 by t. Then this is v1 equal to m2 by m1 plus m2 into root 2g into m1 plus m2 by d. So this can be written as mt into root of 2g by m1 plus m2 into 2. So finally this is the solution. v1 is m2 into root of 2g by m1 plus m2 into d.